This is Mrs. James. This is part 3 of our wave sessions for our end of course exam review. The last thing that we talked about was wave behavior. We learned words like frequency, wavelength, the velocity of a wave, amplitude, constructive and destructive interference, and diffraction. So we're going to move on, and we're going to start talking about something called the electromagnetic spectrum. We really aren't going to be talking about sound anymore for right now. And the electromagnetic spectrum is sometimes called radiant energy. When we talk about the electromagnetic spectrum, we're specifically talking about transverse waves. And remember, those are the ones that look like this. Except that that's a horrible picture. All those waves should be the same size. So pretend I made those all the same size, alright? Alright, remember, transverse waves do not require a medium, and a medium is matter. So they don't need air, they don't need water, they don't need slinkies, they don't need springs to travel. They can travel through the vacuum of space. So they can come from the sun. This would be an example of a natural source of electromagnetic radiation. They could be man-made. A light bulb or a tanning bed is something that we make that creates electromagnetic radiation. Alright, here's a little chart to show us electromagnetic radiation. Notice that I'm showing waves here that have a very small wavelength, high frequency. And as it goes, the wavelengths become bigger and the frequency becomes lower. Notice that their amplitude is not changing. We could be talking about a variety of different amplitudes. So if it's light, it could be brighter or dimmer. We don't really care about that. What we care about is the wavelength and the frequency. Now, I could take all the people in this room right now and I could line them up based on their heights. And I would call that a spectrum based on heights. Or I could line you up based on your GPA. And that would be a GPA spectrum. All I've done here is I've taken all the different kinds of energy that can come from the sun, and I've just arranged it in order of wavelengths. Alright? The wavelengths that are very, very small, they also happen to be very high energy, we call gamma rays, and they all behave the same kind of a way. Waves that have a slightly shorter wavelength, slightly longer wavelength, we call X-rays. Waves that have a slightly longer wavelength we call ultraviolet. And then there's a little tiny range of wavelengths right in here. Look how small that range is. This has made it bigger just so you can see it. That's the electromagnetic radiation that we can see. We call that visible light. The purple waves are a little bit longer than ultraviolet. Ultraviolet, by the way, is what gives you a suntan. So let's take a little note up there. That's what gives you a tan, or skin cancer also. Now, infrared waves, some infrared waves are what keep you warm. So we refer to that as heat energy. It doesn't all not all infrared radiation do we sense as heat, but some of it we do. So we have kind of short wavelength waves, which we call ultraviolet. Then we have purple, which is a little bit longer, going all the way through red, which is longer still. And then we have infrared waves, which are even longer. Microwaves are longer still, and radio waves are even longer. All I have here is a different image, so I'm showing these a different way. This has got the chart flipped. So it's got our long wavelengths on the left. Here's our visible. They're getting shorter and shorter and shorter and shorter, all the way up to gamma waves. By long, these waves are about the size of a house. By short wavelengths, these waves are smaller wavelengths than the nucleus of an atom would be. Alright, so the wavelengths that we can see are about bacteria size. And again, the longest waves that our eyes can see are red, and the shortest waves that our eyes can see are the violet ones. Alright? These are red are a little bit lower energy, violet are higher energy. Gamma rays are super high energy, which is one of the reasons that they're so dangerous and they can cause cancers, also can be used to treat cancers. And radio waves are the lowest energy ones. Again, this whole thing is called the electromagnetic spectrum. Alright, 3 vocabulary words you might want to know. These, I'm sorry, I'm rushing. Let's go back here. Again, these can all come from natural sources, or we can make all of these. We make these on purpose. We make visible light with, say, a flashlight so you can see things. We make ultraviolet tanning beds so people can get a tan. We make x-rays to x-ray people. We make gamma rays to treat cancer. We make radio waves to carry signals from a radio station to your radio. So at the radio station, a machine changes the sound waves into radio waves. The radio waves travel through the air from the station to your house, and your radio turns them back into sound waves for you to hear. And we make microwaves to cook our food. So we make and use all these different kind of waves. We're going to talk about the electromagnetic waves a little bit later on when we talk about astronomy. So our entire astronomy section is really about the electromagnetic spectrum. Alright, 3 words you should know: opaque, transparent, and translucent. What these words are talking about a object's ability to either absorb or transmit electromagnetic waves, specifically light. If something is, we're going to start here, number 1, if something is transparent, that means when light hits it, it just goes through it. A great example of that would be glass. None of it's absorbed. If an object is translucent, we'll call that one number 2. If it's translucent, some of the light gets absorbed and some of it gets transmitted. Remember, what gets absorbed gets turned into heat. And a good example of that would be the shower curtain that I have hanging over my window in my classroom. And some things are opaque. If something is opaque, that means that all of the light gets absorbed and none of the light gets transmitted. My door would be a great example of that. All that light gets absorbed. Alright, let's focus on reflection for a minute. Sometimes light hits a rough object and sometimes it hits a smooth object, and we want to know what happens differently for those two. Alright, here's an example of light rays hitting a smooth object. Here comes the rays. Here they are. They're bouncing off at the same angle. When this happens, these light rays hit your eye in an organized pattern, and it gives you a really good reflection. A mirror is a great example of something that's very, very, very smooth and reflects the light in these parallel rays. Now, sometimes the light hits an object that's rough. So this light is coming in, it's bouncing off the same angle. But this light is hitting at a different angle and it's bouncing off at that same angle. So it goes this way and this light goes that way. This light ray hits at this angle, it bounces off. So you can see this light is getting scattered. So even so, though this object might reflect a lot of light and might be shiny, you can't see a reflection in it because all these rays are going in all sorts of different directions. Alright, so 2 extreme examples of what can happen when light is reflected. Sometimes it's reflected and it makes a reflection like your face in a mirror. Sometimes light is reflected but you can't see an image because of the way that the light is scattered. Alright, the Doppler effect. When an object, we're going to focus right now first here. And you're going to want to copy these pictures into your notes. When an object is creating waves, and let's focus on sound for a while since we've been talking so much about light. So here's our object, we're looking down. This is representing crests. Troughs are here in the middle. Here's our object, it's making waves. They're radiating out in all directions with a constant wavelength, and here you are as the observer. Now here we have an object that's moving while it's making the sound waves. So these waves are getting compressed and these waves are getting stretched out. So if you're here as the observer, as it's coming towards you, the sound waves are very close together, which means they have a low wavelength, high frequency. And as it passes you, you hear these stretched out waves. They have a high wavelength and a low frequency. Well, these are going to have a higher pitch and these are going to have a lower pitch. And that's why when things go past you, the sound that they make, like a race car, is because you hear the higher pitch and then the lower pitch back here. That phenomena is called the Doppler effect. And that is a good place to stop.